Bismillahirrahmanirrahim. Today our lab is implementation of multiplexers using different ways on Verilog HDL. So first of all we have to see what is multiplexer. The multiplexer, the basic diagram of multiplexer is shown here. In multiplexer we have multiple outputs but only one output. So we can control that which input we have to obtain at the output by using the selection lines. Here control 1 and control 2 are the selection lines. When selection lines both are 0 0, we can obtain the input 1 at the output, and when the control 1 is 0 and control 1 is 1, then we can obtain the input 2 at the output. Here we use the NOT gates, not control 1, not control 2, to obtain the negation of control 1 and control 2. Here are the 4 AND gates, one each for the one output. Here you can see the for first AND gate W, the input 1 and the control 1 bar and the not control 2 bar. So when both the control 1 and control 2 are 0 0, so by using these NOT gates, here on the AND gate not control 1 and not control 2 reach, which is 1 1, and input 1 is also 1, so this AND gate will give us the 1 output and this will appear on the output. All these X, Y and Z AND gates give the 0 output, so at the result we will obtain the input 1 at the output when both control 1 and control 2 are 0 0. Similarly, when control 1 is 0 and control 2 is 1, then we will obtain the X1 and it will obtain at the output. So when the control 1 0 and control 2 is 1, we will obtain the input 2 at the output, and similarly for the input 3 and input 4. So in this way the MUX performs its operation. Now we will see how we can implement MUX and Verilog HDL by different methods. So our first method is gate level implementation. The syntax remains same as the Verilog HDL code. First of all we have to declare the module name and all outputs and inputs. Then we declare the output. We have only one output in MUX, so output is 1, which is out. Then we have the following inputs in the MUX: input 1, input 2, 4 inputs and 2 control lines, control 1 and control 2. And similarly then we declare the wires, which are not control 1, not control 2 and WXYZ. Then in gate level implementation we have to assign each gate with the inputs and outputs. So first of all we have two AND gates. Here you see on the screen for the control 1 and control 2. So we can use here the NOT, which represents the NOT gate, and then in the brackets we have declared the first we have to declare the wire or the output. Here we have used the wire, so I written here the NOT control 1 wire, and then comma, and then we return the input for which we have to obtain the negation. Similarly for the NOT control 2, NOT represents the operation which we have to perform, and the NOT control 2 is the wire, which is, we can say that it is the output of the operation, and control 2 is the input for which we have to perform the NOT operation. And then after the NOT gate we have 4 AND gates. Here you see on the screen we have 4 AND gates, and the outputs for each AND gate, and we can say that the wires of each gate are W, X, Y and Z, and following are the inputs. So syntax remains the same. First we have to write the gate name and then in the brackets first we have to write the output or the wire name. Then we have to write the inputs all inputs of the gate. First of all, we have to write the output or wire, and then inputs, all inputs. And similarly for second AND gate, the out wire is X and the inputs are input 2, not control 1 and control 2. Similarly for the third AND gate, the wire is Y and the inputs are input 3, control 1 and not control 2. And similarly last AND gate, which is Z, and its inputs are control 1 and control 2. So this AND gate will give the high output when both inputs control 1 and control 2 are high. And at the end on the figure you see that we have the OR gate, whose inputs are 4, which are W, X, Y and Z, and it's a single output. So here we write the OR gate name, which represents the OR gate, and then first of all we have to write the output of the gate and then the inputs of the gate. This is the syntax to write the gate level implementation, and then our code ends. We have the end module. Here you can see the explanation of this code line by line. Here I have explained all this code by just line by line explanation. You can see here the explanation of every line. Now we have to implement this code, but not for MUX but for the DEMUX. The code for MUX is given. Now we have to change this code for the DEMUX on Verilog HDL. I will show you the one gate level implementation for multiplexing Verilog HDL and show you the how these waveforms appear. Here I have just copy and paste this code for the multiplexer using gate level implementation. Then I compile this, and after that I generate the waveforms, and here are the output and input waveforms. Here you can see that control 1, control 2 selection lines, and then inputs. We have 4 inputs for multiplexer: input 1, 2, 3 and 4, and single output. When our both control lines are 0, 0, then output is following the input 1. Input 1 appears the output terminal. When the control 1 is 1 and control 2 is 0, then the input 3 appears at the output terminal. And when the control 1 is 0 and control 2 is 1, then the input 2 appears at the output terminal. And when both the controls are 1, 1, then input 4 appears at the output. So in this way we can perform the multiplexer on Verilog HDL, where we have 4 inputs and only single output, and based on these selection lines our output appears, whether it is input 1, input 2, 3 or 4. Now we will form code for the demultiplexer using gate level implementation. To write the code of the DEMUX, first we have to understand what is DEMUX. Actually DEMUX is the opposite of multiplexer. In DEMUX we have only single input, which is data here, and 2 selection lines, same as the MUX. S0 and S1 are the selection lines here, and we got the 4 outputs here: Y0, Y1, Y2 and Y3. So we can say that the multiplexer is the opposite of multiplexer. Here we have only one input, and by controlling the selection lines we can obtain that single input on any one of the outputs. If both selection lines are 0, 0, we can obtain that input on the Y0 output, and when S0 is 1, 0 and S1 is 0, when the S0 is 1 and S1 is 0, we can obtain that input on the Y2 output. This is the logic of demultiplexer. Now we are using this logic to write the code of demultiplexer on Verilog HDL. See that I have write the code for the DEMUX gate level implementation. The syntax remains the same as the multiplexer. Example I have already shown you. Here I declare the module with the outputs and all the inputs. Then I declare the outputs. In DEMUX we have 4 outputs, y0, y1, y2 and y3. And inputs we have single input and 2 control lines, control 1 and control 2, and then the wire not control 1 not control 2, same as in the multiplexer. Then first we have 2 NOT operations. First NOT operation is on the control 1 input and its output is not control 1. So this is the syntax to write the code for any gate. First we have to write the name of the operation NOT, then we have to write the wire name or output first and then the input next, and same is the for control 2. And then we have the AND gates, 4 AND gates. First AND gate is for the y0 output and 3 inputs. When input 1 is 1, not control 1, not control 2. When all these inputs are 1, then we obtain the output at the y0. And then for the y1 output AND gate, when input 1, not control 1 and control 2 are 1, then we obtain the output at the y1. Same as the case for the next 2 outputs, y2 and y3, and then our program ends. Now we have to start simulation of this program. Here the simulation starts. We have to wait for few minutes to complete this simulation. Now our compilation for the DEMUX is complete. Now we have to make the waveform, and here we have to give the inputs to the and I select all the dots. Okay, now I say I given the high at the control 1 and low at the control 2, and similarly input 1 is 1. Now I will set the time period for the inputs. I will select it. I will get the input 50 time period, control 1 100 and control 2 to double of control 1 200. Now I will run this. The simulation starts. Here you see that this is our output. On the waveform we see that when the control 1 and control 2 both are 0, then we are obtain y0 output, and when our control 1 is 0 and control 2 is 1, then we obtain the output at the y2. Similarly, when our control 1 is 0, control 2 is 1, we obtain the output at the y1. And similarly, when both inputs are high, then we obtain our output at the y3. So this is the operation of DEMUX. By using the control 1 and control 2 inputs, we can obtain the output at only one output, whether it will be obtained by y0, y1, y2 or y3, based on the selection of control 1 and control 2. So we can implement the demultiplexer using gate level implementation. So our next method is logic statement implementation. Now we see how we can implement the MUX using logic statement implementation. Here is the example of MUX. First we have declared the module name multiplexer, 1x4 multiplexer, and all the inputs and outputs. Then we declare the outputs and then the inputs. We have multiple inputs and multiplexer. And then in logic statement implementation we have to assign the output which is equals to what. In logic statement we write all the logic that we see on the pic here. First we have the for input when output equals to input 1, AND gate, not of control 1, not of control 2. These are all AND gates, then OR with the this all AND gates. Now we use this logic in the program. Here you see we have the single output, which is equals to what? Which is equals to input 1 and with the not control of 1 and with the not control of 2. Then OR with the what? With the input 2 and with the not of control 1 and with the control of 2. Then OR with the input 3 and control 1 and not control 2. Then OR with the final gate, which is input 4 and with the control 1 and with the control 2. If any of these is 1, then we obtain the output 1, because these are OR operations. If any of these is 1, then we obtain the output. When this is 1, then our input 1 will go to the output, and when this whole expression is 1, then input 2 will go to the output, and similarly for these two expressions. Now we have write the code for the logic statement for multiplexer. Now we see how we will implement this method for DEMUX on the Verilog HDL. Now we will see the code for the demultiplexer. On the screen I have written the code for the demultiplexer by using logic statement. Here first of all I have declared the module, then output and input, same as the syntax. Then I have assigned logic statement for the output y0, y1, y2 and y3. Here I have written the logic statement for the y0, which is equals to input and with the not control of 1 and with the not of control 2. When this whole is equals to 1, then our input is equals to y0 output. And then for the y1 logic statement, when input and with the not of control 1 and with the control of 2, when these are going to 1, then we obtain the input as the output y1, and same is the case for the y2 and y3. Now I have already simulated this code. Now I will just perform the waveforms, and I have to select all the nodes. Now I am giving the time period. Now we will run this. Here you can see our simulation is complete. Now when both control 1 and control 2 are 0 0, then we are obtain the output at the y0. It is high and all other outputs are low. And when the control 1 is 1 and control 2 is 0, then we will obtain the output at the y2 and all other outputs are 0 0. And similarly, when both the control 1 and control 2 are 1 1, then we obtain the output at the y3 and all other outputs are 0 0. So this is our logic statement for the demultiplexer. Now we will go to our next method. Now our next method is case statement implementation. Same as we perform is in C++ language, same as in Verilog HDL. Here the module, same syntax for the input and declaring the outputs, and then we register output, because here output will always change depending on the cases. Then we apply always statement on the input 1, input 2, 3, 4 and control 1 and control 2. Because this is case level implementation, so we have to apply case on control 1 and control 2. We are applying the case on control 1 and control 2 because depending on the inputs of the control 1 and control 2, we are going to obtain the output, whether it will be input 1, input 2, 3 or 4. So we are applying the case for control 1 and control 2. These are the case statements. First case is when both control 1 and control 2 are 0, 0. So we will obtain the output 1, which is equals to input 1. Next case is when control 1 is 0 and control 2 is 1. Then we will obtain the output, which is equals to input 2. And similarly, next two cases, when in control 1 is 0, control 1 is 1 but control 2 is 0. Then we will obtain the output, which is equals to input 3. And our last case, when both control 1 and control 2 are 1, 1, then we obtain the output, which is equals to input 4. And here we have the default statement. When display, please check control bits. When any of these cases are not, then we are going to apply the default statement, and that we use the add case where we have to add our these cases. Now we will see how we can implement the DEMUX on Verilog HDL by using DEMUX case level implementation. See that I have written the code for the demultiplexer by using case level implementation. All the syntax remains the same to declare the module, output and input. Here you see that I have the register statement on the outputs y0, y1, y2 and y3, and then the always statement on the input control 1 and control 2. Then we have the following cases on the control 1 and control 2, because control 1 and control 2 are going to select whether we have to obtain which output. When the control 1 and control 2 both are 0, 0, then our y0 output is equals to input. And when the control 1 is 0 and control 2 is 1, then we are going to obtain the y1 output. And when control 1 is 1, control 2 is 0, then y2 output is equals to input. And similarly, when both the controls are 1, 1, then we obtain the output at our y3. And this is the default statement which will apply when we have not any case in these. Then we are going to apply the default statement, and this our case ends and then the program. Now our simulation, I have already simulated this program. Now I will just form the waveforms to check our outputs. Start simulation. Our next case is using the if statement. Here you see the code for the multiplexer using the if statement. The syntax remains the same for the multiplexer. First we have to module the input and output, register and always. The difference is that here we use the if conditions. If condition works in such a way that if select equals to 0, then our output will be equal to D0 input, and if select equals to 1, then we obtain our output, which is equals to D1 input. Same, if select equals to 2, then we obtain the output, which is equal to D2 input. This is the if statement. If statement works in such way. By using the selection, we apply here a statement on the select input. Based on the selection of select input, we choose which input we have to obtain at the output. Now we will see this on Verilog HDL. Now here I have write the code for the demultiplexer using the if-else condition. The syntax remains the same to write the code, but just we have here if conditions on selection, because selection lines select whether we have to obtain the input at which output terminal. Now here you see the if conditions on the selection lines. If select equals to 0, then we obtain our output at y0 terminal, which is equals to input. If selection equals to 1, then we obtain our output at the y1 terminal, and same for the if selection equals to 2 or selection equals to 3. So in this way the if condition works to select the selection length and then obtain the output. I have already compiled that program. I will just create the waveforms. I have given the time periods to our input and output. Now I will simulate it. Our simulation complete, and here you can see the output waveforms of our demultiplexer. Same is the case for all other cases. The output remains the same when the selection line both are 0 0, then we obtain our input at the y0, and when the selection lines are 1 0, then we obtain our input at the y2 output terminal, and same for the y3 and y1. Now we'll see how we can implement the demultiplexer using the if-else condition. Now we will move to our next condition. Next statement is using the conditional statement. Here we see the example of the conditional statement of multiplexer. You see that the syntax remains the same, all module input and output. Here we declare the wires for the output and selection. Here I assign the output q, which is equals to 1, select equals to 0, then d0 input will appear at the output. This question marks appears that when select equals to 0, then d0 will go to the output. Then semicolon, semicolon means or. If this condition not true, then if select equals to 1, then d1 input will go at the output terminal. Then or if both of conditions are not appear, then if select equals to 2, then d2 input will go at the output terminal, and if any of these three conditions are not true, then automatically d3 will go at the output. This is the conditional statement. Now we'll see the code for demultiplexer using the conditional statement in Verilog HDL. See that I have applied the demux using the conditional statement. All the syntax remain the same. We have just write this to conditional statement. Assign y0 equals to when selection equals to 0, then input obtained at the y0 output terminal. Assign y1 equals to when selection equals to 1, then input at the y1 terminal, and same for the y2 and y3. I have already compiled that program. Now I will just generate the waveforms. start the compilation. You see the output of our demultiplexer. The output remains same on all the cases because we have applied the same 1x4 demultiplexer. When the selection lines are 0 0, we obtain our input at the Y0 terminal, and when all the selection lines are 1 1, then we obtain our input at the Y3 terminal. So in this way we can perform the demultiplexer by using different methods. We have seen all the methods from which we can apply the multiplexer and demultiplexer in Verilog HDL. So in this lab we will see how we will perform any operation by using these conditions: if else, always, case statement, conditional statement, or gate level or logic. We can perform any operation, whether it is multiplexer, demultiplexer, or any other. We can generate these by just applying these statements. So that's enough for today lab. Thank you.